So where did all this mass come from? I don't know. But this is a speculative mechanism that I developed and put forward in my thesis. What the geological information tells us for the very early Archean era was that certainly mantle temperatures were around about 1,500 degrees hotter than what they are now, and surface temperatures were between 30 and 300 degrees hotter than what they are now. I'll just briefly mention something about geological time before we go on a little bit further. Geological time, to measure geological time, there's certain minerals that you can assay and determine they decay. They're decay products, they're daughter elements. You can measure the ratios of these, and you can then convert that to time. You know the decay rate of these various minerals, and there's a whole suite of minerals that you can use. And these methods are very, very sophisticated these days. I work at Telfer in central north West Australia at the moment, where our rocks, we have granites, they're dated at 604 million years old, plus or minus 1 to 2 million years. And this is very, very accurate compared with 10, 15 years ago, where that would be 600 plus or minus 20 or 30 million years. So it's becoming very, very sophisticated and very accurate these days, what I digress. So what I was alluding to is you can only measure the age of a rock once that the crystals in that rock have solidified and that rock has cooled enough to be preserved with time. So at that moment in time when that first rock solidified and was preserved up to the present day, and you then go and measure that, take measurements from that. Prior to that time, if that rock was molten, you cannot measure time. So basically our geological time starts at that moment when that first rock crystallised and solidified and preserved to the present day. So these high mantle temperatures and surface temperatures then suggested to me that during the pre-Archean, prior to 4,500 million years ago, for an indeterminate period of time, that the Earth was actually molten. And what I've shown here in this first one is a slightly larger Earth, an Earth plus Moon incandescent blob. And what I intimated in my research was that the Earth, this primitive Earth-Moon blob, was very much closer to the primitive young Sun, very much smaller than what it is now, and totally different to what it is now. So if you can imagine a fragment, or not a fragment, a blob of material flung off the surface of this primitive young Sun, very similar to the sunspot activity that we see today on a yearly basis, happening on the Sun today, but different materials. So what I'm suggesting is that we have this whatever the Sun is made of, this blob of pure energy, whatever, plasma, whatever, that's flung off this surface of this Sun. That blob, as well as periodically the remaining planets, are also the same. This material, this primitive planet, along with the other planets, then gradually, over a very extended period of time, move away from the surface of the Sun, away from the influence of that high temperatures on the Sun. This material, this energy, then simply condenses to form matter. This is simply a reversal, as our next speaker I think will allude to. This energy, in Einstein's equation, if you increase the speed of matter, you convert it to energy. If you decrease the speed of energy, you condense it to form energy. It's just simply a reversal of Einstein's equation. Energy has no mass, or matter has mass. So at that moment in time, once that energy condenses to form matter, you then start to get mass. During this same phase, I envisaged this newly formed material condensed on this very primitive blob of Sun material, becoming gravitationally unstable, or generating a wobble. I calculated that if you need 400 kilometre thickness, which is about that scale of material, of this new molten matter, to be stripped off that primitive Earth-Moon blob to form a binary Earth-Moon planet, which is what we are now, a binary planet. The size of the Moon and the size of the primitive Earth were roughly identical dimensions at that time, 1,700 kilometres radius, 3,400 kilometres diameter. We'll forget about the Moon now. That Moon comprised matter which had already been condensed. So the radius of the Moon essentially stayed constant from then on. The Earth was still retained this highly reactive core material. I then envisaged this condensation of matter to continue to condense at the core mantle interface. New material will then forming the mantle. New material will then cause mantle swell. Mantle swell will then be transferred to the outer crust and cause crustal extension. By the time we get to the Permian period, we then reach a point where this newly formed continental crust, the ability to extend is exceeded, and we start getting fragmentation and breakup of this crust and opening up of the modern oceans. And this is a cross-section of the modern Earth, where we have mid-ocean rift zones, volcanic material being derived, upwelling from the mantle, being extruded along these cracks and being solidified on the sea, at the ocean floor. The fragments of the continental crust remain in position with deep roots. This is again a contentious issue in plate tectonics, where the continents have very deep roots, where in plate tectonics this material is supposedly subducted in this very region where we have these deep roots, very, very deep, hundreds of kilometres deep roots below our continents. So that's in a nutshell